I don't need this. I don't need this anymore. Or this. Okay. All right. So I need to label each one of these as to what kind of S it is. So like this first one, since I'm in n equals 1, that's why this is called 1s. Since this is n equals 2, that's why this is 2s. And you may want to write these if you can on your periodic table because it will help you come up with electron configurations in a little bit. This is 3s, 4s, 5s, 6s, and 7s. Okay, I don't know if I can erase. You used to not be able to do this.
Should be included on the bonus question.
I'm not telling you anything else about the bonus. The bonus is just quantum numbers. What I'm doing right now has to do with teaching you electron configurations. Okay. Okay. Now, in terms of labeling the P's, since this is the n equals 2 energy level, this would be the beginning of 2p. This is 3p, 4p, 5p, 6p, 7p. Okay? And then the D's are one behind the period that they're in. Energetically speaking, they are slightly closer to the nucleus. So if this is n equals 4, this is not the beginning of 4D. This would be lagging one behind. So this is 3D, 4D, 5D, and 6D. Okay? And then the F's lag 2 behind the period that they're in. Think of the F's as this accordion that I can sort of like smash up. And this fits up here, actually. This fits right up here. So if this is n equals 6, you can see the 6 right here. 2 behind 6 is 4. So this is technically the beginning of 4F, and then this would be the beginning of 5F. Okay? Now, we use the shells, n equals 1 through 7, and the subshells, S, P, D, and F, to describe where electrons are seated or located outside the nucleus. The number of electrons that you can fit in each subshell, S, P, D, or F, is predetermined by the number of like boxes that you have in each subshell. For instance, in 1s, I have 1, 2 boxes that I can fill, so I can hold 2 electrons in 1s. 2s holds 1, 2 electrons. 2p holds 1, 2, 3, 4, 5, 6 electrons. Okay, 3s holds 2. 3p holds 1, 2, 3, 4, 5, 6. As you fill them, you have to start with the lowest energy subshell first because it's closest to the nucleus. So you have to fill 1s first with 2 electrons. Then you're allowed to start filling 2s with 2 electrons. And then you can go to 2p with 6 electrons, and then 3s, and then 3p. You get the idea? Like you're reading a book. Okay? Then you would fill 4s. You've got 2 spaces. 3D has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces, so it can accommodate 10 electrons. Okay? So, in general, the S's can hold a maximum of 2 electrons. The P's can hold a maximum of 6 electrons. The D's can hold a maximum of 10 electrons. And then the F's have 14 boxes, so they can hold a maximum of 14 electrons. Okay? This is known as writing electron configurations. Okay? Okay, so we're going to, let me see here. We're going to go back to your book. Let me know when you're ready. So let's go over here and let's see what we're missing here. So we did this. We did this. I want to highlight something on this page for you. As a shortcut, you want to know how to identify the number of orbitals in an energy level n. N squared tells you how many orbitals exist in an energy level. Okay, so let me explain that by going back to your periodic table here. Okay, so in n equals 1, 1 squared would be 1. So I would have 1 orbital. Orbitals hold a maximum of 2 electrons. And this makes sense because I have a 1s subshell in n equals 1, so I would only have 1 orbital. Orbitals are typically drawn as boxes. So you would see something drawn as a box and they would write 1s underneath it, and that box is your orbital. Okay? If I'm looking at n equals 2, for n equals 2, 2 squared is 4. So that means you have 4 orbitals in n equals 2. Okay, where do they all come from? Each s is 1 orbital because it holds 2 electrons, okay? But if I've got 6 electrons that can fill a p, wouldn't I need 3 orbitals to accommodate those electrons? Do you see what I'm saying? So each one of these boxes is an orbital. Each p has 3 orbitals. We typically draw them attached to each other. And each one of them can hold a maximum of 2 electrons. Okay, so the reason why I have 4 orbitals in n equals 2 is because I have an orbital for these electrons in 2s, and then you would have 3 orbitals for the 6 electrons in 2p. And I'll be drawing all this out. Okay, if we're looking at the Ds, if I can hold 10 electrons in a D, how many orbitals would I need? 5. So you would have 5 boxes attached, and you would have 3D underneath it. You can accommodate your 10 electrons in those 5 orbitals. Okay, for the Fs, if I have 14 electrons, how many orbitals would I need? 7. Okay. All right, let's go back to the book. Let's come over here. This table outlines the number of subshells in each n. So this column is my n. These are the subshells that exist in it. And then these are the number of orbitals that I have, which comes from n squared. So 1, 4, 9, 16, based upon the energy level being squared. Then underneath here, you've got this figure showing you the energy diagram for hydrogen, meaning n equals 1 is here, n equals 2, n equals 3, n equals 4. You will notice the further away you get from the nucleus, the closer each n gets to the previous one. Okay, and that's what I drew on the board. Let's take a look at the next page. Let's come over here. We talked about the magnetic spin quantum number. That's how an electron spins up or down. That is bonus. And then that leads us to here, the Pauli exclusion principle. Okay. So what I'm going to start doing is teaching you how to write electron configurations, and we're going to have to use some basic principles. Electrons all exist in a unique place. This is known as the Pauli exclusion principle. So I can't describe an electron with the same set of quantum numbers because each electron is in a unique location. I would know that if you're trying to calculate the maximum number of electrons that can exist in an energy level, you would do that by using the equation 2n squared. And then let's go to the next page and let's look at the Aufbau principle. When I told you that when we're filling those subshells, we have to fill them with the ones that are closest to the nucleus that have the lowest energy. This is the Aufbau principle. So we fill the lowest energy subshells or orbitals first, and then we move up from there. Okay, so now we're ready to do these electron configurations where I'm going to use the N, and then L is the subshell, S, P, D, or F. And then in the upper right-hand corner, we're going to write a number which indicates how many electrons are located there. Okay? I'm kind of throwing a lot at you, but once we start to do it, it'll make sense. And then I'm going to draw the electron configurations as orbital diagrams, which will look like this. And then that's essentially the whole section. So let's come back to this periodic table. And let's do some of the basics first. So let's say, let me make this bigger. Do I have that option? Maybe. Yes, I do. Okay. All right, let's start with the basic one. Let's start with hydrogen. All right, this is the beginning of 1s, okay? Hydrogen has 1 electron in the 1s. So the electron configuration would be 1s1 for hydrogen. The 1 is the N, the S is the shape S, and then the 1 in the upper right-hand corner tells you how many electrons you have there, okay? If I'm looking at helium, helium requires me to cross over. Here's hydrogen. Here's helium. We had crossed out this hydrogen here, okay? Helium has got 2 electrons. Those 2 electrons would have to be in 1s, so I would write 1s2. Okay? Then for lithium. Lithium is down here in 2s, but lithium has a total of 3 electrons. The first 2 electrons have to be up here. We have to fill the 1s first before you can put the 3rd electron in 2s. So we would write 1s2 for the first 2 electrons, and then I have 1 electron in 2s. So after that, I would write 2s1. Okay? So that means when you add up this 2 and this 1, that gives you 3 electrons total. Okay? And then when I'm looking at beryllium, beryllium is here. Beryllium has a total of 4 electrons. That's this number in the upper right-hand corner. But you have to describe the first 2 being seated at 1s. So I would have to write 1s2. That has to be filled first. Then I can move on to 2s. I have 1, 2 electrons in 2s. Okay? You don't have to put this circle around the 2. Not necessary. Okay? Oops. Let's move on to boron. Okay, boron is over here. It has 5 electrons. Where would I describe the first 2 as being?
1s2.
Yeah, 1s2. And then the next 2 would have to be in 2s. So I would write down 2s2. And then you will cross over. This is the beginning of 2p. I have 1 electron in 2p. So I would write down 2p1. What if I was doing nitrogen? Walk me through that one. Where are the first 2 electrons?
1s2.
1s2, okay. The next 2 would be?
2s2.
2s2. And then you would cross over. We have 2p1, 2, 3. Okay.